Today we want to discuss atomic fusion and whether it can or cannot be our energy resource of tomorrow. In this video we'll cover what atomic fusion is, the basics and how it works, and also where it happens, and we'll look at the conditions now, so how far have we researched atomic fusion, and we'll take a specific look at fusion reactors, and in the end we'll do a prediction when we'll be able to use atomic fusion as an energy resource. We'll compare pros and cons, and also we'll compare atomic fusion to other energy resources. So what exactly is atomic fusion? Atomic fusion means the fusion of two atomic cores to one new one. And when we talk about atomic fusion in terms of nuclear energy, and especially nuclear fusion, we mean fusion of hydrogen atoms. And we are able to do that because of a phenomenon called tunneling. And in the result of this fusion, there is a high amount of energy released. But you can also see on the chart on the right that there's some fusions that actually need energy to be put into, and these are the endothermic fusions. And you can also see that the fusion of hydrogen is the reaction where most energy gets released. Okay, so we talked about using hydrogen atoms for our atomic fusion, and specifically deuterium and tritium. And under the influence of high temperature and high pressure, both of these isotopes merge together to a new atom, helium, and a neutron. And while this happens, there is lots of energy released. There is 14.1 megavolts released with the neutron and 3.5 megavolts released with the helium. And you can actually calculate how much energy is released by Einstein's formula. So the energy equals the delta of the mass times the light speed squared. This atomic fusion happens at different places, and we have the stellar atomic fusion on one side, which is actually the role model of our fusion reactors. This is where we got the idea from, so to say. And we have our fusion reactors where we try to do it artificially. So let's take a look at stellar atomic fusion first. It happens in the interior of stars, and it is where or how the main energy is produced, so that's why they emit that much light and that high temperatures. The mass effect of the proton-proton chain is 0.635%, so you can calculate the energy that is released. And there's actually different types. So on the right side you see a proton-proton chain 1, and that's actually the fusion that needs the lowest temperatures, so it also happens in our sun. Another fusion type is the so-called CNO cycle, but it only happens in larger stars where the temperature is higher and also the pressure is much higher. Okay, so let's do an example calculation with our sun. So the delta in energy, so the change in energy, is equal to the change in mass times the light speed squared, as I said. So the mass before minus the mass after times the light speed squared. So in the case of the sun, this is we have 564 million tons of hydrogen per second, and the mass effect is 0.635%. So if we multiply all that, we get to 3.22 times 10 to the power of 26 joule. And the energy demand of the Earth is just 505 times 10 to the power of 18 joule. So in 1 second, the sun releases enough energy to supply humanity with power for 637,386 years.
Now we want to start talking about the fusion reactors and what actually happens inside those. First of all, it's very important to know what the hydrogen goes through. So we have the solid stage, in which it is in the coldest. After that, it becomes liquid, and in the end into a neutral gas. If we raise the temperature even higher, it becomes a so-called ionized gas, which is also known as plasma. In the fusion reactors we use today, or we experiment with, the plasma gets heated up over 100 million degrees Celsius. So let's start talking about fusion reactors itself now. First off, I'd like to concentrate on the tokamak. Later on we're also going to talk about the stellarator, but for now the tokamak, which is the older one of the two. Here the plasma is held in place through magnetic coils, obviously, and what happens is the plasma itself gets a current. This current has to be increased at every state in time, so the coils actually produce a magnetic field, and the magnetic field line itself turns. Why is it important that the magnetic field line turns? Otherwise, the magnetic field on the inside of the donut would be way stronger than on the outside, and the whole thing would collapse. So that's why we have these many coils, and we have the plasma current, which is run through the tokamak. The big problem, the always increasing current can't happen at some point in time anymore. So we don't have infinity amount of energy which we can put through the plasma, which means the tokamak can only last a very short amount of time, and which is a very big contra argument to the tokamak. So as I said, the tokamak is not a fusion reactor yet, which actually supplies the world with energy. So what is the goal of fusion reaction actually? The goal is to generate energy in form of electricity. Right now the status is that we have to put more energy into the reactor than we actually get out of it, which is obviously not good. But if we achieve this goal, we are less dependent on fossil fuels, because all of electricity will be generated by atomic fusion, and we have more sustainable energy resources. Okay, but let's talk about the operations. So how is this all going to work? As I said before, plasma has to be heated up over 100 million degrees Celsius. But at the same time, it has to be kept in place by the magnetic field, which in the tokamak is done by 3 magnetic coils. But as I also said before, the big problem is that the magnetic field has to get stronger and stronger, through which we have to put more energy into, and for that we need a solution. So let's improve the efficiency, and let's talk about how we get there. Well, first of all, the heating needs a lot of energy. Obviously 100 million degrees Celsius is a very high temperature, but the good thing about atomic fusion is that once it has started, it can keep itself alive. So that is the big part, how we can save energy by heating it, because as in the sun, the fusion keeps on going and going without any energy put into it in the end. But also the gas needs to be turned into plasma, which also obviously falls under the aspect of the heating aspect. But a very big problem as well is we need to add the hydrogen atoms, because at some point from the start there's going to be the hydrogen atoms are going to be fused to helium atoms, and from that stage on we need to add more hydrogen atoms, and that is also a big problem because we can't just walk into the reactor, because obviously 100 million degrees Celsius is a very high temperature where no human being can even be near it, but also no material itself. So how do we add these hydrogen atoms into the reactor is also a very big question which we are confronted with. Okay, so as I said before, we're also going to talk about the stellarator, and here we compare the two types of reactors we have in the world nowadays. So one, as we already mentioned and described, is the tokamak, and on the other hand it's the stellarator. The stellarator is the newer one of the two and has only been able to build through modern computer technology. Why is that? Because the coils, the magnetic coils on the outside, have to have a very certain shape for it to work. And why is this? As I said before, the plasma gets a plasma current inside the tokamak. Inside the stellarator, that's not the case. The magnetic field lines, which also here have to be circular, so the magnetic field isn't stronger on the inside than on the outside and the whole thing collapses. These magnetic field lines are produced through the magnetic coils in the stellarator. This is obviously very positive because we don't need to put more energy into the reactor itself as it keeps on going. But as I said before, these coils are ones that humans couldn't find out how the shape was, so that's why this is a very new one, and the newest one is in Greifswald, Germany. So yeah, here the plasma gets the plasma rotates itself, and through rotation of the plasma a magnetic field is also produced, which cooperates with the magnetic field through the coils, and through that the plasma can be held in place. But also here there are a lot of contra sides, as for example, as I mentioned before, adding hydrogen atoms into the reactor itself, or the high temperature is also here a problem. So it's still not a reactor which lasts very long, and we still have to put more energy into it than we can get out of it, but yet it is a better concept, which most people say right now, than the tokamak. But still the tokamak is built and researched on because informations we get out of both reactors are very important for the further knowledge for atomic fusion. Okay, as a conclusion now, let's bring it all together from the tokamak and stellarator. So we have the different structures. Obviously, in the tokamak we have 3 different types of coils, in the stellarator only 1. The operation works completely different as well, whereas in the tokamak we put a current through the plasma, which always has to increase to keep the magnetic field that comes from the current alive. In the stellarator we don't have that, because the magnetic field itself, generated by the coils, has a circular structure, or gives the plasma a circular structure, which leads to the effect we need, and that on the inside of the stellarator the magnetic field is not stronger than on the outside. Problems: tokamak, as we said already, we can't increase the current over a large amount of time, but there are many problems both of the reactors have, and for example that is the problem that the high temperature can't be converted always, or can't be kept in place. Although we have the magnetic fields, we are operating with a very high temperature, which is very hard for us to keep in place. Next thing is that we have a little amount of radiation, but that isn't the biggest problem. And on top of that, the biggest problem itself is obviously that we can't add, or maybe it's not the biggest problem right now, but it's one of the big problems, that we can't add hydrogen atoms while the fusion is running. And what we want to do a certain amount of time for us to convert, or to get the energy out of it, is keep the whole system alive, or the reaction, and that can only happen if we add hydrogen atoms to it. And that is, as I said, one big problem which we still have to solve, but we aren't at that stage yet that we can actually think about the problem yet, because we don't have the ability yet to keep the reactors running that the amount of time that we actually need to add hydrogen atoms. So we wanted to see, with 1 liter of water, how much energy can we generated out of it, and with the obviously the equivalent of lithium in the Earth's crust. So yeah, lithium, the isotope we need, is included in the Earth's crust, only is a very small amount, but still enough. So we need 1 liter of water. That was the thing we wanted, and then according to that, the equivalent to 26.05 kilograms of Earth's crust. And through a calculation we did, we got out of it that we would generate enough energy to be able to drive around the world one whole time with an electric car. Now we want to calculate how much water we would need to generate the whole energy, or the energy demand of humankind nowadays on Earth. So yeah, the energy demand per year is 505 times 10 to the 18th joule, and the energy we get from 1 liter of water and 26 kilograms of rock is 9.4 times 10 to the 9 joule. That equals that we would need 5.7 times 10 to the 10 liters of water to generate the whole demand of energy we need in a year. To put it in comparison, we took the German Bodensee and took a look at how much water is actually in the Bodensee, and it's about 4.8 times 10 to the 13 liters of water. And let's divide that by our yearly demand of 5.7 times 10 to the 10 liters of water. We get out of it that we would have enough water only in the Bodensee to generate energy for 842.11 years.
Okay, so let's summarize now and take a look at the pros and cons. On the con side, we have the questionable usage. We cannot be sure yet whether we will be able to use atomic fusion for our power supply. And there also is some radiation. We also have expensive development right now. We have very high cost and don't get anything out of it yet except for research purposes. And if it will be usable, it will only be usable in approximately 30 to 50 years up to a standard to actually help our power supply system. But the pro side is very big as well. We have the efficiency in terms of what materials we use. We have a low half-life of the radiation, so we don't have the disadvantage that we have with nuclear fission. And we have the material fatigue, which is not that high. And we can actually have 24/7 usage, so we're not dependent on any other circumstances. The availability is almost endless. We have enough of the sources we need. And there's no harm done to the environment through CO2 emissions. And there's no maximum credible accident, as in the nuclear fission, for example.
As said in the beginning, we're going to compare the atomic fusion to other energy resources we have nowadays. So yeah, let's start off with hydroelectric. There's no CO2 emission and radiation, which is obviously very good. But as other energy resources, we cannot get the energy upon need, and that is also a very big contra from wind and photovoltaic. The next contra-argument to other energy supplies are the CO2 emissions. In biomass, that is the case where we put CO2 back into the atmosphere, which were at once generated out of it, which is okay, that's why we put it in brackets. But in lignite or hard coal or natural gas, if we burn those energy resources, that's where CO2 comes back or goes into the atmosphere, which obviously is very bad for our environment. And in nuclear fission, that is where we have a very high amount of radiation, and a big catastrophe can happen if something goes wrong, like we've seen, for example, in Chernobyl. So if we compare fusion to all these energy resources we have today, we have barely any radiation, or let's say radiation which we can control very easily and cannot resolve in a huge catastrophe. We have no CO2 emission, and we have energy upon need, so we can get the energy out of it at any time. And that is obviously a very big pro, because that is the only energy resource we have, or we know about today, which has all these pros to it. But as you see here, nowadays fusion doesn't make any percent of the energy supply in Germany. But what we want to achieve is that one day that there will be a very high number that comes from fusion.